Hi, everybody, and welcome to another episode of Echo Live. Let's see. Let's do an audio test. Can anybody hear? All right, we'll switch our microphone back over again. I swear I did all my tests today and my microphone has been working fine all day long until, of course, it comes time for Echo Live. Apologies if you missed the very beginning of the program. I've now switched my microphone over. It's a little bit echoey. This one's just not quite as nice as my other microphone, but it is fail-proof, and so hopefully you'll be able to hear me. Now, today we're going to be teaching you some science tricks using the most important chemical on planet Earth, which is water, or H2O. So all of the experiments we're going to teach you today on Echo Live are experiments that you can and you should try at home. We'll teach you a little bit of the science behind them so that you can use these water tricks to impress all of your family and friends with how much you've learned here on Echo Live. If you haven't done so already, feel free to send me a comment or a chat on whichever program you're watching through. That comment or chat feature is your way to communicate with me throughout the program. You can ask and answer questions. You can let me know that I'm muted if that happens again, because I am seeing them, and that is very, very helpful. So thank you to everyone for tuning in, and let's get started with our very first experiment. Now, we're calling this one the unpoppable balloon. And we said that water has something to do with all of our experiments today. So I've got a good spread of balloons just over here on our table, and I'm going to go ahead and put on my safety goggles. Now, all of these experiments are safe for you to try at home. You'll notice I'm not wearing my lab coat today because we're not working with any sort of dangerous chemicals. I'm going to put on my safety goggles because it's just good lab safety practice. Because for this one, I'm going to be taking my balloons and I'm going to be lighting them on fire, or really just using the lighter and holding it up to the balloon. So you can tell me in the chat, what do you think is going to happen if I were to light my lighter and then bring my balloon close or touching the flame? What do we think is going to happen to this balloon? What do we think? What do we think? Tell me in the chat, give me your hypothesis. What do we know about balloons? They're full of air, right? They're pretty squishy. They're normally made out of some combination of latex and rubber, which allows them to grow to many, many times their original size. So go ahead and tell me in the chat. Lots of guesses starting to come in. And you tell me you're pretty confident that if I touch the balloon here to my lighter, it's going to pop. So the balloon definitely popped. It only took a second or so, right, for that balloon to get hot enough that the combustion reaction took away those elastic properties of our balloon, and it caused it to pop. Let's see. Oh, right. So that's happening because the flame is very, very hot. It actually causes the latex in the balloon to melt, which forms a hole, right, and it lets the air seep right out, causes that big popping noise as we hear the air rushing out of the balloon. So let's give that another try here. Ooh, my lighter will light. But you'll notice something interesting is happening with this balloon. Although I'm holding it nice and close, it took 2 or 3 tries, right, for me to get this balloon to pop. So we have some balloons here. These ones are just full of air, like this orange one. Oh no, I might have gotten my lighter wet. There we go. And they pop very, very quickly. But I've got one more balloon that's got water inside it, right? And before we try this balloon, let's talk about the science behind what's happening. You'll notice it took me 2 or 3 tries of really heating the balloon in order to get the red one, which was full of water, to pop. That's because water has the highest specific heat of any liquid that we've ever discovered. Now, specific heat is a measure of how much energy it takes in order to raise the temperature of a substance by 1 degree Celsius, or to raise 1 gram of that substance by 1 degree Celsius. Water specific heat is about 4.2, which is extremely high. We said that's actually the highest specific heat out of any substance that we've ever discovered, any liquid substance, that is. This has a lot to do with the arrangement of these water molecules. So we've got a diagram of how water molecules move within a liquid. We know that in a liquid, these molecules have some energy. They are flowing past each other, which means that the hydrogen bonds between the water molecules are constantly breaking and forming, and breaking and forming. Bonds, especially hydrogen bonds, take a good deal of energy in order to form and be broken. Since it takes energy to do that, when we heat water, we're not just heating the water. Some of that, right, is going towards that process of breaking and forming hydrogen bonds. Liquid water, those bonds are extremely unstable. They're constantly changing. When we have solid water, they're rigid. Those bonds are fixed. But the reason that water, liquid water, has such a high specific heat is because of those constantly breaking and reforming hydrogen bonds. So the energy doesn't just go straight into heating the substance. It has to be split between those two processes, between heating the substance and making and breaking hydrogen bonds. If we take a look at this diagram, oh, there's my diagram. This diagram shows us the specific heat of various substances here on Earth. So things like gold have a very, very low specific heat. It does not take very much energy to raise the temperature of gold. There aren't hydrogen bonds inside gold, or inside solid gold at least. And so there's really, all the heat can focus on raising the temperature of that substance. Air also has a pretty low specific heat, which is why the temperature can change very quickly outside depending on if it is sunny or if it is cloudy. But as we go down the chart, you'll notice that specific heats get much higher. So our specific heat starts to climb. And if we were to change our units, so when we measure specific heat in joules per kilogram, we say it's about 4,200. Normally we would measure it in joules per gram, which would drop this down to 4.2, like we said. That's the common way we would describe it. And if you look at something like wood, the specific heat is even lower than water, right? And so the specific heat is different for all these substances because of how much energy it takes in order to heat or cool them. Now, if you've ever been outside at the beach or near a swimming pool, you might have dipped your toes in the water in order to cool yourself off. That's you taking advantage of the specific heat of water. If the specific heat of water was very low and it was really easy to change the temperature of water, right? The water should be the same temperature as the air outside. So there'd be no benefit to sticking our toes down in the water. But since it takes much more energy, the water will stay cooler for much longer than the air around it. Now, if you've been to the beach, right, you've ever walked along the sand can get very, very hot, so hot that sometimes you need to run over to the water and dip your toes down inside, right? That's again because of the specific heat. The specific heat of sand is very, very low, meaning that when it starts to get warmed by the sun, it gets hot very quickly. It's easy to change the temperature of sand, but water, we say, is a great insulator. Since the specific heat is so high, it can actually withstand that change, or that addition of heat pretty well. So if we do this one last time, and we're very careful about where we place the dark balloon, makes it hard to see where my water is. But you'll notice that even when the balloon is touching the flame, it takes much longer, and I have to heat that same spot many, many times in order to get the water hot enough that it absorbs the heat and then it's transferred over into the water balloon. All right. So in addition to water being a great insulator or having a very high specific heat, water also has amazing surface tension. And we've got a couple tricks that we can do using that amazing power of surface tension between water. Basically, surface tension relies on the properties of cohesion and adhesion, which are two big words, but they're very important when we talk about the properties of water. If we think back to our diagram of what water looked like, water really wants to stick to each other because of those hydrogen bonds. We call water sticking to itself cohesion. You can think of it, just like it's sticking to all of its friends. We call that cohesion or, cohabitation if it was people existing all in the same space. That's water sticking to itself. But water will also stick to other polar objects. It will also stick to other things that it's able to be attracted to because of its polar nature. So where the hydrogen atoms are positively charged. Where the oxygen atom is, it's negatively charged. And that allows it to try to stick to other polar substances as well. So water sticking to itself, we call cohesion. Water sticking to other things, we call adhesion. And a good way to remember that is that you say that things adhere to one another, but you wouldn't really say they adhere to themselves. So using an adhesive like glue allows you to stick two different things together, right? So adhesion is two different things. Cohesion is one type of thing sticking to itself. Now, a pretty fun trick that you can try based on this principle of cohesion and adhesion is called the string bridge. So I've got some red water here inside this beaker, and I'm just going to go ahead and pour it into one of these plastic cups. All right, so no trick there. The water is inside the cup. But if I were to take this cup and hold it right where it is and tilt it towards the ground, right, the water's just going to pour right out. The object of this trick is to get the water to pour from this cup into this cup without holding them over one another, right? So we really have to overcome the force of gravity for this one. And we can do that using that property of cohesion and adhesion. So what we'll need for this is a string. It wouldn't be called the string bridge if we didn't have a string. But it's important that the string is wet, that it's soaked up a little bit of water before you try this experiment. That way it's going to allow the water molecules to adhere to the string. Duct tape works great for this because it can stick to things even if they're a little bit wet. Any sort of tape would work, but duct tape is definitely the easiest thing that you could use. So we're going to go ahead and tape one end of our string bridge to the first cup. Just right inside. And then we'll take the other end of our string. It would help if my hands weren't wet for ripping this duct tape. There we go. We're going to take the other end of our string bridge and tape it to the inside of the opposite cup. Now, this trick might take you a little bit of practice, but the principle is, right, that the water really wants to stick to itself. And so it wants to stay together, and it will do that if you give it a medium to travel down. And so the string is the medium in this case. And I'm going to hold the cups just like this, and I'm just going to pour slowly. Make sure my string is totally stuck to the paper, or to the cup there. I can see it starting to move. All right, let's give this a try. And hopefully you can see that as long as I pour very, very gently and very slowly, that although my cup is pretty far off to the side, the water is traveling right down the string. Now, this trick isn't perfect because, like we said, the properties of cohesion, of the water wanting to stick to itself, is much stronger than the properties of adhesion, of water molecules wanting to stick to something else, like the string. So you might see it start to drip off the string just a little bit. If the water droplets get heavy, right, they are more likely to stick to each other and form a droplet than they are to stick to the string and keep traveling down in a nice, neat line like they're doing right now. But as long as you pour slowly, right, those water molecules will adhere using those hydrogen bonds to the damp string. Nice and slow, nice and slow, nice and slow. And let's see just how much of that water we've now transferred over into the other cup. So really with very, very little spilled here onto my tray, we've transferred almost all of the water from this cup into this cup. And it's just something that you have to try with a little bit of patience, right? But this all has to do with the amazing surface tension of water. And we see this in real life all the time. We see this in nature quite often. If you've ever seen a bug called a water strider, maybe on the surface of your pool, or if you live near a lake or a pond, water striders have this amazing ability to walk on water. And that's all thanks to surface tension. It's really nothing to do with the bug at all. They don't have superpowers, but they are light enough that they're not able to break through the tension that's exhibited by the water molecules at the surface. So you can see that we have a diagram here, right? And these arrows represent bonds, and they represent a direction of force as well. So where the arrows are, we have hydrogen bonds holding together these water molecules. We call that cohesion. And then we also have the arrows, which are a direction of force. So they're pushing on each other. And as long as that force is greater than the force of gravity pushing down from our water strider or our object on the surface of the water, right? That surface tension is able to allow these bugs to walk on water, which seems like a pretty amazing feat. Unfortunately, humans are a bit too dense and we can't distribute our weight quite enough to act like water striders and to walk on water, but we can use it for different sorts of tools and machines that we've built, all just based on that property of water that it wants to stick to itself. Another experiment you can try at home, kind of a science game, is trying to see how many drops of water you can get stacked on top of just one penny. So we're going to zoom way in over here. And what I've learned is if I stick my hand right behind here, I can get the camera to focus. Oh, we want to go this way on my pennies. And so you'll see that I have 3 pennies. I chose a good variety of pennies. So I have one copper penny, which is a penny, right? We've talked about this in the past, that was made before 1982. And so this is an old penny that's completely made of copper. This one in the center is a Canadian penny that's also made completely of copper. And then we have a newer penny from 2016 right here. And the results won't be wildly different, but it's not an experiment, right? If you aren't changing some sort of variable. But this experiment is going to also show us the amazing surface tension of water. So if I again put my hand right here, should get the camera to focus. There we go. And let's go ahead and see just how many water droplets I can get on the surface of each penny. Does anyone have a guess? How many drops of water do you think I can get on the surface of each penny? So let's see, I'll show you one drop if you need it for reference. So here is one drop on the surface of the penny. How many drops do you think this penny can hold? Ooh, lots of people guessing. They know the surface tension of water is pretty amazing. So we see guesses for 60 or 100. Jennifer and Jennifer both tell me 20. All right. Good guesses, everybody. So we did 1. Let's keep adding and we'll count one by one. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh no, we're having them leak off the edge. All right, well that one held 13. Let's try our next penny. I'm a little disappointed in those results. Maybe I need to add a bit more gently. All right, here we go with the Canadian penny. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. All right, the surface of the penny is now completely full of water at 21 drops. But let's see, 22 seems like the maximum for our Canadian penny there, but we've got one penny left. Scoot these ones off to the side. I don't want my water to spread into my penny because we said that water loves to stick to itself. So if we have water touch the outside of our penny, or if our penny gets damp, that could cause the results of our experiment to get skewed, right? We want the penny to be completely dry to start with, and then we only want the water to be joining or touching this other water droplets on the surface. If we give it water on the side to stick to, it will want to. All right, let's try this again. 1, 2. Ooh, you guys, I am not doing well with this today. Let's go ahead and try this one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh no, 16. All right, you guys, my luck is not going so well with pennies today. We got at least 21 on our Canadian penny. So it seems like our guesses for 20 were the most accurate, but I'd like for you to challenge yourself to try this at home. See if you can get even more water droplets on the penny. I know that it's possible. It's not working for me quite so well today. Maybe I'm shaking my table a bit too much, but I would love if you tried this at home. Tell me how many drops you're able to get just balanced on the surface of one penny. You'd be amazed at how large you're going to be able to grow that bubble of water, that structure of water on top of the penny. It will be much larger than the surface of the penny because those water molecules don't want to let go of each other. They want to stick together. And so you can actually get a huge, really tall water bubble to balance on top of each penny there. All right, we've got one last experiment for our round of water tricks today. This one we like to call the glasses are half full. So if you've ever heard the phrase, right, is the glass half empty or glass half full, we're going to kind of do an experiment about that topic here. So what I have are two identical glasses. I chose clear glasses so that we can see the water inside. And what I'm going to do is I'm going to fill them both all the way to the top with some water. And this is just water. Again, I've dyed it purple just so that we can see it a little bit better, and because I personally believe that science is always more fun when it's a little bit colorful. So we've got one glass completely full to the top with water. Let's fill our other identical glass. It's important that if you try this at home, that you choose two identical glasses. All right, so we've got both of our glasses now full all the way to the very tippy top. And then I have our laminated card, which we've used in the past for our gravity fail experiment. And I'm just gonna go ahead and use it so that I can move this glass of water and balance it right on top of the other identical glass, and trying not to lose any of our water. It's okay if you lose a little bit, but you wanna keep as much in there as possible. And then we're just going to remove the card. Trying to keep them lined up. We want them to be totally lined up, trying to keep as much of that water between our two glasses as possible. So minus the small amount of air in the top of my glass, which I lost as I moved them or transferred them over to each other, right? We have water inside or trapped inside these two glasses. But of course, gravity is trying to pull the water out of the top glass, right? It's trying to pull it down towards the ground through any sort of opening that we give it. But what's amazing is I can actually shift my glasses apart from each other ever so slightly. And right now, there is actually a small gap between the two glasses. So let's zoom in and see if we can see, or at least notice that right here. Let me turn off my virtual background to see if that's helpful, even though I think it looks super cool the way it is right now. All right. There is a gap right here on the side. So there's actually a small amount of space where the water is exposed to the air, which means that there's an identical one over on this side. but the water is staying in the glass. It's not leaking out, right? We can attribute that to that property of cohesion. The water wants to stick to each other. And since there's air pressure pushing on the surface of the water, just like when we have a water strider balancing on the surface of water, right? That surface tension can withstand a fair amount of force or a fair amount of pressure, which is exactly what's happening right now. Even though the water is exposed, it is able to leak out. Since the opening is so small, the cohesion between those water molecules are causing or are not allowing the water to leak out. But what we're going to do, and the challenge in this activity, if you were to try this at home or challenge your friends to this science trick, is how can we remove the water from the top glass without moving it or without touching it. And so for this, you'll just need one tool, a plastic drinking straw, really any drinking straw, so that we can blow air across the surface of that gap. I'll do it just for a second here so we can take a look at what happens. So even with just a very small amount of air, right, without touching the glass at all, we're able to break that surface tension. We are able to displace an equal amount of water for the amount of air we blow into the glass. So it takes a small amount of force. You don't want to blow too hard because you certainly don't want to disturb your glasses. They're balanced very, very carefully here. And you definitely want to do it over some sort of container, right? Because as soon as we break that surface tension, the water or the air from the straw wants to rush inside the glass. It wants to fill that space inside the glass, and it's going to displace the water inside. So all you need to do is just take your straw and very gently blow across the surface to break that surface tension. And there you have it. Now our glasses are half full. So we have one full glass, right, and one empty glass, which if we were to combine them, right, our glasses are now half full, thus the name of this science trick. So that's it for our H2OMG water tricks that we've got to show you today. If you have questions about how you might recreate these experiments at home, tell me in the chat. If you have suggestions for experiments or science tricks you might like us to explain or teach you, send those in the chat as well. We love hearing your suggestions and bringing you new programs based on the things you want to hear about. As always, we are so appreciative of our donors like Ford and Denso who allow us to bring these programs to you for free every single weekday. We will be back here tomorrow at 2:30 with even more Echo Live. And if you are looking for activity guides for science experiments that you can try at home, visit the Michigan Science Center's website. We've got all sorts of activities about water, about chemistry, about physics, things that you can and you should try at home, just like these. Let's see. Stephanie asked, does the water have anything in it that makes the bugs float in a pool or a lake? It doesn't have to, right? Really, the reason that those bugs are able to walk across the surface is the bonds between those water molecules. So water is really the thing that we're looking for. There obviously are other things inside lakes and pools, especially, right? Chemicals. And those chemicals could actually lower the surface tension of water because they might interrupt or interfere with those hydrogen bonds. It would take a lot of chemicals, right, to displace enough water, which would probably make the water unsafe to swim in or maybe unsafe for even the bugs to be touching. And so thankfully that doesn't really happen, but it really is just the property of water itself that allows bugs and other objects to float on or walk on the surface of water because of that surface tension. All right, good question. Does the size of the glass matter in the last experiment? No, you can try this with any glass. Remember that the glasses need to be identical, so you need to choose two glasses that are exactly the same so that you can line up the two openings together, but you can use any glasses. I would recommend starting with something small. Make sure you get really good at balancing them on top of each other before you move on to something bigger. Plastic would be great because if they did happen to topple over, right, they're not going to break. These are glass, which means I had to be very careful in my rounds of practice, or you could always do them on top of a softer surface, something that's not going to cause anything to shatter if it does fall. Great question. Lots of people sending great suggestions. I would love to talk about dogs. If you have any specific questions about dogs that you'd like us to talk about, let us know. I'd love to talk about dogs. I am, of course, a cat person. You've met my cat a couple times now, but I would love to talk about dogs. They are so awesome, and please keep sending these suggestions. Can you put any color water in the balloon and then pop it? Yes. So the food coloring does not lower or raise the specific heat of the water by any sort of it's a negligible amount if it does. So you can color the water. You don't have to color the water. Of course, if you are going to let the balloon pop like I did, make sure that you do it outside or somewhere where you're ready to clean it up. All right. Thank you everyone so much for joining me. I hope I'll see you back here tomorrow for even more Echo Live. We've got a very